right, today we are going to be talking about Sir Isaac Newton and his laws. We are also going to focus on gravity, motion, and momentum. All right, so this is Isaac Newton. I am sure you've heard about him before, and we've talked about him in 6th grade as well. He was one of the greatest scientists and greatest mathematicians that has ever lived in the entire world. He was also the first person to hypothesize that the force that would pull an apple towards the ground would also keep the moon in orbit and around and toward the earth, which is something we know to be true today of both items, both the apple and the moon. Gravity is our key topic here. So Isaac Newton was the first person who actually did a serious study and understanding of the idea of gravity. He suggested that it was a force that attracted all objects towards one another or towards each other, which would indicate why the moon was attracted to the earth and the earth attracted to the sun. The force is measured in a unit called newtons, which you should be familiar with from the unit before where we talked about force and motion with net force. And basically, the distance between the second two objects is 3 times larger than the distance between the first two, and the two images here, we see 1 million kilometers versus 3 million kilometers. Therefore, the strength of attraction between the second two objects is 9 times smaller than the attraction between the first two, noting that it would go by 3, 6, and 9. Gravity is going to be the greater the distance, the less the force. So the closer an object is to another object, the stronger the gravitational pull will be. Hence why the gravitational pull of a planet such as Neptune would be less than the gravitational pull of the planet such as Mercury. The greater the mass, the greater the force. Again, makes sense. The greater the object is in size, the greater the force that it's going to have behind it or upon it. So if you have 10 billion kilograms versus 1 billion, or 10 billion versus 2 billion, you'll notice the product of the first two objects would be 10 billion, while the product of the second two is 20 billion. Therefore, the second two objects is going to be 2 times or twice as strong as the first. I would highly encourage you to watch this gravity video that you can find on Discovery Education in your notes. It's a great way to review gravity and get more information. All right, gravity and acceleration. Objects fall to the ground at the same rate. We know that to be true. It's been proven. We know, and that's because of acceleration due to one thing, gravity. Gravity is the same for all objects on the earth. It doesn't change just because an object is different. This stop action photo shows that you have a table tennis ball, which is ping pong ball, and a golf ball, which is the white ball in this picture, and they fall at the same rate even though they have different masses. The ping pong ball is much lighter, the left ball that is blue, than the golf ball that is white on the right side. They do have different masses, but again, because of gravity being the same for all objects, they fall at the exact same time. Acceleration of an object towards the earth is going to always and forever be 9.8 meters per second, or meters per second squared. You need to know this number because it's probably going to show up on the EOC. So for every second that an object will fall, the object's downward velocity will increase by 9.8 meters per second. So if you notice the image here, we start at 0 for our velocity. We move to 9.8 meters per second. We add another 9.8 to get 19.6, another to 29.4, another to 39.2, and another to 49, indicating the downward motion of acceleration because every meter it moves increases by that 9.8. All right, then we have air resistance. So even though gravity and acceleration are going to be the same for the two objects, there are things that are going to work against an object. So example here, why does a feather not fall as fast as a ping pong ball? The air resistance is going to be the opposing force that's going to cause the object to be different. There could be 3 different things here. The force of gravity is going to pull the apple down. If it were the only force, acceleration rate would be 9.8 meters per second squared. But we have air resistance, which is pushing up on the apple, forcing the subtracted from the force of gravity to yield your net force, which is what we've been talking about. So you have 2 forces working against each other here. Because we have that upward force of air resistance, it's not going to accelerate at that exact moment, and the net force will be different. the net force on the apple is going to be the force equal to the air resistance subtracted from that force of gravity. Because the net force is not going to be 0 newtons, the apple accelerates downward, but the apple does not go as fast as it would without the air resistance. So you can see the force is pulling it down for gravity, the air resistance is pushing against it, and then the net force is going to be the overall motion. All right, a vacuum is a place with which there is no matter, okay? This means more like a vacuum seal, think of it that way. There is no air resistance in a vacuum, therefore all objects are going to fall in a free fall idea. Terminal velocity is a great example of this. So it's the constant velocity of a falling object when gravity is balanced by the air resistance. Great way to think of terminal velocity would be like remembering that brain pop we watched where we had Tim and Moby skydiving and they had the motion down until they opened their parachutes and they flew back upward. All right, so if you want to have a fun little experiment, you can do the why does this happen? Take out a piece of paper. Doesn't have to be plain, it can be whatever. Lay it on your desk and put a pen or a pencil on top of it. See if you can pull the pen or pencil out without the pull the paper out without the pen or pencil moving. Think about why this happens and how this has to deal with air resistance. Which leads us into Newton's first law. Newton has 3 main principles or 3 main laws of motion. We talked about them in 6th grade very briefly, and we focused a little bit on all 3 of them, but heavily on the first one. An object in motion continues in motion at the same speed in the same direction unless acted upon by an unbalanced force, which means something is going to prevent it from stopping or changing its motion. In the image below, we have our skateboarding little friend. He hits a rock. When that rock is the unbalanced force that's acting upon it, he stops. He's no longer in motion and he's no longer at the same speed. An object at rest will remain at rest unless acted on by an unbalanced force. Okay, that is the true definition of Newton's law. It's not going to happen unless something causes it to happen. It's not going to stop its motion unless something causes it to stop its motion. So we often call this the law of inertia. Think back to 6th grade, think about things moving forward. Okay, you're going to see some images that will probably be remembered from before. The law of inertia is also known as the law of laziness because basically, why would you move if you don't have to, right? All right, so the law of inertia is the tendency of an object to resist a change in motion. Inertia wants to continue down a straight path, moving straightly forward. This law is the same reason why you wear a seatbelt, because if you slam on brakes for any reason, that sudden change from the unbalanced force is going to cause you to be triggered backwards, such as in this image below. Has the unbalanced force, he's triggered forward. If you wear a seatbelt, you're triggered backwards. All right, some examples in real life to put these in context. We have magician's trick of pulling the plate out from, the tablecloth out from under the plate where the plate does not move. We have, just like in the simulation on the page before, when you ride a horse, if the horse stops suddenly, you're probably going to go flying over it. Just like in the convertible car on the page before, you would fly out of it if you weren't wearing a seatbelt. The car turns left, but you physically appear to slide to the right. The difficulty of pushing a dead car. If the car is dead, it's not going to go anywhere. Why? Because of the law of inertia. And then a football player running with the ball. Another thing that's going to be important within this law is Earth and the moon and the remaining in their orbits. We did a gravitational activity. It was a lab when we were in the 6th grade that focused on this. So basically the 2 things combine to keep the Earth in orbit. Inertia plus gravity equals centripetal force, if you remember to 6th grade. But more importantly, they combine and they keep our Earth in orbit around the sun and our moon in orbit around the Earth. By doing this, they are moving in 2 different fashions. Inertia is going to be pushing forward. Inertia always moves in the same direction. However, gravity is going to pull towards the other object. Gravity wants to pull it towards whatever its focal area is. If we're talking about the moon and Earth, gravitation of the Earth is pulling on the moon. It wants to go in a straight path with a pulled way of pulling in. When it does that, it's going to create a curved circular motion where it's going to curve around the Earth as seen below here. This is moving around because it's technically moving in a straight line here, for inertia, but being pulled in because of gravity. Without it, basically it would crash. Here we go as a great simulation. For the gravitational pull between the moon and the earth, you're going to pull the moon towards the earth. The earth is being pulled towards the sun, but more importantly, the moon would go straight for inertia without gravity, and it would just fly off. Because it has a gravitational field, it's going to pull it towards the object, and it will continue on the orbital path it has. Which brings us to orbiting. Orbiting is when an object is traveling around another, specifically in space. So things like the International Space Station are going to orbit around the Earth. Things like the moon orbit around the Earth. We have put up multiple satellites that orbit around the Earth. All of these are in orbital path. When a spacecraft is going to orbit, it's moving forward because of inertia, but the spacecraft can also be in free fall towards the Earth. So it moves at a constant speed here. If there were no gravity, it would just continue to follow this straight dotted line and never be seen again. The space shuttle is trying to free fall because gravity wants to pull it back. It would not move straight if there was nothing there and it was not traveling forward. But then we have our purple line here, which is the path the space shuttle follows, because when it gets caught in orbit with that gravitational pull, it's going to create that circular motion. Astronauts appear to be weightless when they are in the space shuttle, but they are not, because they are in what's called free fall. So they are in the orbiting spacecraft because of that free fall motion, which means they feel like they are floating and being weightless, even though technically they are not. This is a great video that you can check out, but I don't think it'll let me play it here with sound. So make sure you watch it in the notes. That's all for today.